Okay, so we'll go for the problem here. So now the layout of a shaft carrying two pulleys 1 and 2 and supported on two bearings A and B is shown in figure. Okay, so the shafts transmit 7.5 kilowatt power at 360 rpm from the pulley 1 to the pulley 2. The diameters of the pulley 1 and 2 are 250 mm and 500 mm respectively. The masses of pulleys 1 and 2 are 10 kg and 30 kg respectively. Full point. The belt tensions act vertically downwards and the ratio of belt tensions on the tight side to the slack side for each pulley is 2.5 is to 1. Okay. The shaft is made of a plain carbon steel, so ATC8 with yield strength as 380 megapascal. Okay, and the factor of safety is 3. Estimate suitable diameter of shaft. If the permissible angle of twist is 0.5 degree per meter length, okay, calculate the diameter on the basis of torsional rigidity. Assume G equal to 79,300 Newton per mm square. So now we'll go for drawing the diagram here. I'll go for drawing the diagram. Now this is what support A, support B. Okay, this is pulley number 1. Now this is what pulley number 2. Okay, now we need to find out what is the diameter. You need to find out what is the diameter. Okay, so now in this video just I'm going to give the hint, so how you need to calculate and solve it and have the answer, please. Okay, now before we want to start this one, let us note down given data. Okay, so now weight of pulley 1 is given, it's 10 kg. Okay, so weight of pulley 2 is given, this is 30 kg. Okay, so now assuming G equal to 10, okay, assuming acceleration due to gravity equal to 10, so let us find out W1 equal to 100 Newton, W2 equal to 300 Newton. Okay, so now they have given belt tensions for both. So what tight side to slack side is, it is a 2.5 to 1. 2.5 to 1. That means, so tight side T1 equal to, it is 2.5 times of the T2. Okay, it's 2.5 times of the T2. And also they have given diameter here. Diameter now diameter of this pulley 1 is 250 mm. And diameter of this pulley is 500. Okay, so now power is transmitted to the pulley 1 and power is received by the pulley 2. Okay, power is received by the pulley 2. Okay, next okay, so sigma yt is given. Okay, sigma yt. For TC8 steel it is a 380 megapascal. Okay, and factor of safety they have given 3, and twist angle of twist, it is a 0.5 degree per unit length, okay, and G, that's 79,300. Okay. Now these are the given datas. And power also they have given. Now power they have not specified. Okay, right. Power they have not specified. Yes, they have given power. It is 7.5 kilowatt. Sorry, P equal to 7.5 kilowatt. Speed N equal to 360 RPM. Okay, 360 RPM. Okay. So now let us start solution. Okay. So as the power is given, first you calculate a torque transmitted through the shaft, okay, or torque transmitted by shaft. Okay, so this is what T equal to. So in data handbook you have a standard equations. To calculate the torque if you know the power and speed. Now you can use this equation to find out the power. Okay, sorry, to find out the torque. Okay, in SI units. So now power has to be substituted in terms of kilowatt. Okay, so now referring design data handbook. Okay, so from design data handbook, so referring equation number 3.3a, we'll check whether right or wrong. Okay, 3.3a, T equal to 9.55 into 10 to the power of 6 into P divided by N. Okay. So some book they have added the one more factor here. There is what a CS. So CS refers to the service factor. Some book they have added it CS service factor. Okay. If they have not specified CS, then you take it as a 1. CS equal to 1. Then you calculate. Okay. Now in this case, torque T equal to 9.55 into 10 to the power of 6. Okay. So power is a 7.5 kilowatt divided by speed is 360 RPM. So you just calculate how much you are going to get. Okay. So once you got the power, then you can find out the tension in the pulley 1 and tension in pulley 2. After getting tensions, you can find out what is the maximum bending moment is going to be subjected. Okay. So let us go for next the calculation of tensions. Okay. So tensions in pulley 1. Okay. So let us go for T equal to, okay, T equal to R1 in bracket T1 minus T2. R1 minus, okay, so R1 in bracket T1 minus T2. So now this equation I think you have studied from either in Tom 1 or in Tom 2. Just remember this equation. Okay. Now what is the value we are going to get here from torque? You just substitute back here. Okay. Now for case of R1, where the radius of pulley is 125 here, okay, Now we can substitute T1 equal to 2.5 times of T2 minus T2. Now if you solve this equations, you are going to get the value of T2. Okay? Once you got the value of T2, then you calculate value of T1. Value of T1. Okay? Now the net tension acting on pulley 1. Okay, let us go for this as a T11. Okay, I'll go for T12. Okay, sorry, okay, I'll go for T1, T2 here, T1 here. I'll go for T11 here. Okay, so now this is equal to what? The T1 plus T2, you are going to get the net tension of pulley 1. Right? Now, similarly calculate tensions in pulley 2. Similarly calculate tensions in pulley 2. Tensions in pulley 2. Okay, so we'll go for same equation. So now T equal to R2 in bracket, let us go for T3 minus T4 for your clarification purpose. Okay, now for pulley 2, let us consider T3 equal to on tight side, okay, and T4 equal to on slack side. T4 equal to on slack side. Now we substitute the value of T, what you have obtained from earlier equation, from this equation. Okay, let us go for this as equation number 1. Okay, so now this is equation number 2. Now from equation number, you just substitute value of T here, capital T, that is what torque transmitted. Now R2 is how much here? It is a 250. Okay? Now T3 is how much? Is 2.5 times of T4. So now by solving this one, you can just note down. So T3 equal to 2.5 times of T4. Okay? So this is what given data. Now solve for, okay, now you solve for T4 here. Once you got the value of T4, then you calculate value of T3. You get the value of T3. So the net tension. So net tension on pulley 2. Okay. So now for this one, I'll go for T22. T22. Okay. Now this is equal to what? T3 plus T4. T3 plus T4. Now this is what? Fourth equation. Okay. Next, as they have provided, so the transmission of power is vertically downward directions. Right? Now we need to draw the free body diagram. So based on these tensions, okay, let us go for the free body diagram. Or load diagram. Okay. Now, so let us consider this is the shaft here. Okay, so it has a support RA. Okay, it has a support RB. Okay, now the total tension which is acting on left hand side, it is a T11. On right hand side, it is a T22. Okay, now you have dimensions here. Now this is how much? 250, 500, 250. Now we need to calculate what is the reaction force at A, what is the reaction force at B. Okay. Now based on this one, you need to calculate what? Referring this diagram. Okay. So calculate the reaction forces. Okay, you will get RA and RB. Okay, RA and RB. So use equilibrium equations, you are going to get the value of RA and RB. Next, so once you go to the value of RA and RB, next you need to find out what is the maximum bending moment, or what is the, okay, where you are going to get the maximum bending moment, where you are going to get the maximum bending moment. So next, find out, so maximum bending moment, or you can go for bending moment calculations. Okay, bending moments calculations. Okay. So let us go for bending moment at support, at pulley 1. Okay, so if you consider pulley 1, so MBA is a 0. Okay. Next, so bending moment at support A, sorry, at support A. Okay, that is what RA, reaction force. Now you are going to get some value here. You are going to get some value. Okay. Now I will draw the diagram here, considering the only left hand portion. Now this is what a T11. Okay, so you have a support here. This is what RA. Now this is the length. Now this is the length, 250 mm. Okay. Now bending moment at support A. Okay. I'll go for MBA. You can just notify the notations in accordance with. Okay. Now we'll go for this as at left. Okay, left hand. Now at support A, you are going to get some value here. Value is how much? 250 into T11. Okay. Now similarly calculate bending moment at support B. Okay, so that is what at RB. Okay. Now in this case you can go for using the right hand side diagram also. Okay, so to avoid confusion, so we'll start considering only on left hand side. Now we'll draw the diagram here. So now this is what a support B. Okay, you need to consider bending moment at this location. So now bending moment at BB. Okay, at BB, this is what. Now the bending moment because of this T11 causing the hogging. Okay, hogging. Let us go for a minus. Now this is also minus here. This is also minus. Okay. Now here also we are going to get minus 750 into T11. Okay. Then plus RA into 500. Now you are going to get MBB. Just to compare, now I think this is equation number 4. This is equation number 5. Okay. Now we compare. Which point you will get maximum bending moment? You will get maximum bending moment. Okay. Use that value to find out the diameter of shaft. Okay. Okay. Right. Okay. Let us go for you got maximum bending moment at support A. Okay, this is what MBA. Okay. Next, because of this bending moment, what you are going to get? You are going to get a bending stress. you are going to get a bending stress. Okay, so bending stress is sigma b equal to what? M by z. Okay, so now you substitute mb, z is what? Pi dq by 32. Okay? Now instead of using dq and all those things here, you refer design data handbook. So they have written equations in terms of m here. Okay, m plus square root of m square plus t square. Okay? They have written equation in this fashion. So now you better calculate only bending moment. Okay, so they have took pi d cube as outside. They have took pi d cube as the outsides. Okay, so that is what it is going to reduce the confusion, the substitution of d cube value in bending equation and torsion shear stress equation, as well as in bending stress equation. Okay, now let us go for, now let's scratch out this portion. Okay, you got a maximum bending moment is MBA. Now you got a maximum bending moment here. So next I'll find out what is the shear stress. Okay, what is the shear stress because of power transmission? Because of power transmission. Okay, so now let us find out T here. Let us find out T. So already we calculated T here. Already we calculated T. Okay. So you can substitute that T. You can substitute that T. You will get directly d cube. Okay. So now you just go back. You just go back. Okay. Now you have calculated T here. Now you have calculated T. Okay. So use this T in equations. Okay. Now, as I said, you can directly get the diameter. As I said, you can get directly the diameter. Okay. So in this case, as it is subjected to two types of loads. In this case, as it is subjected to two types of loads, you find out the diameter of shaft using maximum normal stress theory or using maximum shear stress theory. Okay. So now let us go for the diameter of shaft. So diameter of shaft based on maximum principal stress theory. Maximum principal stress theory. Okay. So refer design data handbook. Okay. So equation number, let's see what is the equation number here. Okay, you refer equation number 3.5a. Refer equation number 3.5a. Okay, so I'll write here the equations. So d naught equal to 16 divided by pi sigma max. Okay, pi sigma max in bracket m square plus root of m square, sorry, now this is only m. Okay, m plus okay, so this is what m square t square here. Okay, bracket close. Now into, okay, into 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 divided by 1 minus k to power of 4 here. 1 k to power of 4 bracket to the 1 power of 3, bracket to the 1 power of 3. Right here it's the k to power of 4, k to power of 4, right? Now, so sigma max can be calculated as sigma yt divided by fys. Okay, this is what sigma max equal to sigma design stress or sigma allowable stress or sigma permissible stress. Okay, already I have calculated here. Okay, so refer this m, substitute here. T already have got from torque equation. Okay, now k equal to 0 here because it is a solid shaft, because it is a solid shaft. Okay, now you are going to get the diameter. You are going to get the diameter. Okay? So next, based on rigidity, as you need to find out shaft diameter based on rigidity. So when it comes into picture rigidity, so the effect of the bending moment has to be neglected. The effect of bending stress has to be neglected. Okay. So now to get the diameter here, so refer design data handbook, equation number 3.2. Okay, equation number 3.2. Okay. So what is their equation? So theta equal to, so theta equal to 584 GTL. Okay, that is right. Sorry, 584 TL. Okay. 584 TL divided by g d to power of 4 here. Okay, g d to power of 4. Now this is what theta is to be in terms of degree, in degree. Okay. So now we can find out d equal to 4th root of 584 into t into L divided by g theta. Now L has to be substituted as 1000 mm because the deflection is given as 0.5 degree per meter. 0.5 degree per meter.